In this video, we'll solve a few integrals using integration strategies. One of the strategies is rewriting the integrand. So if we take a look at the example where we have to evaluate the integral of sine of x minus 1 over cosine squared of x dx, well, just in the format that we have right now, we don't have a formula. So let's take this advice that we have there, rewrite the integrand. So integral of sine of x minus 1 over cosine squared of x, if we rewrite it in another format, it might be helpful. So I'm going to write it as sine of x over cosine squared of x. And how about I'm going to write cosine squared of x as cosine of x times cosine of x dx minus integral of 1 over cosine squared of x dx. So I chose to actually separate the two integrals, but at the same time, the denominator of the first one, I wrote cosine of x times cosine of x. If I multiply a 1 in the first integrand, of course, it's not going to make any difference. And so I'm going to get tangent of x times secant of x dx minus, and the second integral is secant squared of x dx. Now, if we take a look at the integration tables, we do have integral of secant of x tangent of x dx. It's actually secant of x. And we do have integral of secant squared of x dx to be equal to tangent of x. So going back to our problem, we actually end up getting secant of x minus tangent of x plus c. Well, is any other way we can solve this integral? Yes, we can actually, after we split it, we can use substitution. Maybe we consider u equals cosine of x and go from there. So try to get that advice and solve the integral in a different way. Let's take a look at another one. Substitution after rewriting the integrand. So let's take a look at this problem. Evaluate integral of x squared over square root of 4 minus x to the 6 dx. So when I look at this integral, I think of this integral here. It looks something like that, or even more, it looks something like this one, but it's not really exactly that one because at the numerator we have a variable. But I'm thinking of a combination between this one and what we have here. Now, in the integral that I was telling you about, we have dx over square root of a squared minus x squared, which is arcsine of x over a plus c. But in our case, I don't have x squared, I have x to the 6. But I have x squared at the top. So what if we make this connection? We write square root of 4 minus x to the 3rd, everything to the 2nd. It's still x to the 6. But I can see that if I set u equals x to the 3rd, du is 3x to the 2nd dx, which means x to the 2nd dx is actually du over 3. So going back to our problem, instead of x squared dx, right, x squared dx, we can just put directly du over 3. So it would be 1 over 3 and du at the end. So at the numerator, it's going to be 1 over square root of 4 minus x to the 3rd, now it's a u squared. So now we can see right away that this formula can be applied easily. So it's going to be arcsine of u over 2 because our a, it's actually 2. A squared equals 4, so a equals 2 plus c. But our original problem was in x, so 1 over 3 arcsine of x to the 3rd over 2 plus c. Okay, let's take a look at another problem. We have evaluate integral of 1 plus x squared dx. Now what happens in this problem? What strategy should we use here? So what I'm going to do, I'm thinking of integration by parts. So I'm going to remind you that integral of u dv is uv minus integral v du. So in our case, let's say u equals ln of 1 plus x squared, because the two functions that I can see here are basically ln of 1 plus x squared, and I can consider this times dx. So basically du is going to be 1 over 1 plus x squared times 1 plus x squared prime, which is 2x. And then dv, it's actually the dx, right? So we have two things. We have ln and then we have dx. So the dx is the dv, and v is going to be equal to x. So based on the formula for integration by parts, this is going to be equal to u times v. So x ln of 1 plus x squared. As you can see, we are using parentheses instead of absolute value because the quantity 1 plus x squared is positive, minus integral of v, which is x, times du. Here I forgot to put dx. 2x over 1 plus x squared dx. So let's continue all the way here. So we get x ln of 1 plus x squared, and let's work on this integral, which is minus, I can put the 2 outside, x squared over x squared plus 1 dx. So what I'm going to do, every time we have the denominator having the same exponent, the polynomials have the same exponent as the denominator, we divide them. So x squared divided by x squared plus 1, we get 1 minus x squared minus 1 using long division. So what does this mean? It means that I'm just going to copy x ln of 1 plus x squared minus 2, and I'm going to obtain more terms. So this is why this I'm going to put after that parentheses. So when we divide two fractions, then we can write the answer as the quotient plus the remainder over the dividend. So our quotient, when we divided, we got 1, plus the remainder is negative 1 over x squared plus 1. But let's not forget we were calculating integral of that. So I can put integral of this. Let's continue. So we copy the x ln of 1 plus x squared minus 2 integral of 1, it's x, and then plus 2 integral of 1 over x squared plus 1 dx. So this one is going to give us plus 2, and integral of 1 over x squared plus 1 dx is already a formula. It's arctangent of x plus c. Final answer. Now let's take a quick look at the last problem that I wrote here. Evaluate integral of t squared e to 2t dt. This problem is, well, I changed the variable so that we get used to other variables as well. And this one is pretty much integration by parts. Integration by parts. So, again, integral of u dv is uv minus integral of v du. So in our case, let's decide what's our u and what is our dv. So we will choose between these two functions, the function that it's giving me easier, that can be integrated easier as our dv. So basically e to 2t dt. And then u is t squared. And the next step, du, would be 2t dt. And now I know that we actually made the right choice, because when we differentiated this, we got the power less. So we are decreasing the powers of the polynomial function, so it's going to be easier for us to calculate the integral. And the v, it's integral of that, which is e to 2t over 2. So this integral is equal to uv, which is t squared e to 2t over 2, minus integral of v du, which is 2t dt. So you see how the next integral, it's simpler, right? So we get t squared over 2 e to 2t minus integral of t e to 2t dt. So a lower exponent. If we chose them, if we chose v to be, or dv to be t squared, v would have been t cubed over 3, so we would increase the exponent. So we get t squared over 2 e to 2t, and then minus, and I'm going to do the same thing again. U equals t, du equals dt, dv equals e to 2t dt, so v equals e to 2t over 2. So in our case, it's going to be minus, and so I'm going to write here and open parentheses because I'm going to obtain two terms, which are uv, so t e to 2t over 2, minus integral of v e to 2t over 2 du, which is dt. So now we can simply see how we get t squared over 2e to 2t minus t over 2e to 2t, I'm opening the parentheses, plus I can pull out 1 over 2, and integral of e to 2t, it's e to 2t over 2, so I'm going to make it over 4 here. So what happened? We actually integrated by parts twice. Now, what do you think about the integral of t to 100 e to 2t dt? Well, think about that. How many times would we have to integrate by parts? I hope this helps.